In our previous unit, we used simple distance equations and piecewise functions to explore the relationship between distance and velocity. We found that velocity could be found through the slope of the distance function, and that distance could be found by taking an area under the graph of the velocity function. We also found that velocity is directional, meaning positive velocity corresponds to increasing distance, while negative velocity represents decreasing distance, or distance in the opposite direction. The only way to represent increasing or decreasing velocity, the act of speeding up and slowing down, is through a velocity function with a slope, which represents acceleration. Both velocity and acceleration could more generally be called rates of change, as they represent how fast the results of a function change over the course of a domain. These concepts are not necessarily special, it's just physics after all. But distance, velocity, and acceleration are a good way to think of rates of change, as they are something we also absorb in the real world. We noted the rate of change of distance is velocity, the rate of change of velocity is acceleration, and in general, if a concept can be expressed as a linear function, the rate of change will be a constant value, the slope of the line. In this unit, we avoided talking about the rate of change of nonlinear equations, such as power functions with a degree of 2, 3, or anything other than 1. This is because, unlike linear functions, a function with a curved graph will have a different value for the slope if recorded between different sets of 2 points. So we can't define the rate of change of a curve as a constant. As far as we know, it's an infinite set of constant slopes. It may not even be fair to call the results of these formulas slopes, since a visualization of the line formed by the points we're using shows that we're barely matching the actual path of the graph. To summarize then, our two current challenges with the slopes of curves are 1. Accuracy, since the slope formula isn't really built to deal with curves, and 2. How to describe infinite slopes as a singular value. To begin, let's work on the accuracy issue. Taking the slope between any 2 points on something like x squared produces a line that typically cuts through the parabola, missing some of the change under it. When we use an inaccurate line to estimate slope, we call it a secant line. How can we make our secant line more accurate to the slope of the curve? Let's try making the 2 points closer together. Closer points connect to make secant lines that are much more accurate to the shape of the curve. If lowering the distance between the points makes a line that more accurately resembles the slope of the curve, then what would the most accurate distance be? Logically, the ideal distance between the points would be 0, basically taking the slope at a single point, or instance, on the graph. This is an instantaneous rate of change, which is the first key to figuring out the slopes of curves. The most accurate slopes are instantaneous, meaning they are recorded at a single point on the graph instead of across 2 points. When the line changes this way, it transforms from a secant line to a tangent line, and the slope of a tangent line is equal to the slope of some other graph at a particular x value. So we may know what we want now, the slope of the tangent line at a single point, but trying to use the slope formula with a single point involves subtracting the coordinates of the point from itself. This will always produce a slope of 0 over 0, which is undefined. This would imply that there is no slope at any single point on the graph. But when we just talked about tangent lines, we figured out that there should be something. Since the slope formula seems to be at odds with this conclusion, the question becomes, how can we trick the slope formula to give us a slope for an undefined distance? Let's try something. Why don't we lock one of our 2 points down to a single coordinate, 4 and 16? Because 4 squared is 16. The slope from 4 to 5 is 25 minus 16 over 5 minus 4, which equals 9. Now, let's repeat this process with a closer point, like x equals 4.8, and y would be 4.8 squared, which is 23.04. This slope makes 7.04 over 0.8, which is 8.8. 4 to 4.6 is going to give us 5.16 over 0.6, which equals 8.6. These slopes are more accurate to the correct slope directly at x equals 4, but we can definitely get closer. Let's try 4 to 4.1. Here we get 0.81 over 0.1, which is 8.1. 4 to 4.05 gives us 0.4025 over 0.05, which is 8.05. 4 to 4.01 gives us 8.01. If we repeated this process with numbers that were below 4, such as 3.5, 3.9, and 3.99, we'll get slopes of 7, 7.8, and 7.98. Both of these sets of slopes seem to suggest that if we are able to get a slope exactly at 4, the answer should probably be 8, and your assumption would be correct. This means that if we want to find the exact slope at a point, we need to take the slope with a close by point and just sort of round our answer off. The closer the 2 points, the more accurate your answer will be. This still is an exact process though, because as we saw, the slope formula simply cannot give you the most accurate answer because of the division by 0. The reason we can ignore this fact is because of our newest calculus concept, the limit. The shortest, simplest definition of a limit is the answer that you should get even if you're not allowed to. This is why in most situations, limits are typically equal to y values. For instance, the limit as x squared approaches x equals 2 is 4, since 2 squared equals 4. The only time a limit is anything significant is when you're attempting to find answers that are not technically there. For example, the rational equation x squared plus 8x plus 15 divided by x plus 3 looks pretty complex, like it might produce a wild graph. But it actually makes the least complicated type of graph we know, a line. This is because the numerator of the expression can be factored down to x plus 3 times x plus 5, allowing the denominator to cancel out, leaving y equals x plus 5, which is just a linear equation. When we scroll over this graph a little bit, we notice something strange. There's a hole in the graph. How could this be? The truth is quite strange. When you simplify an equation with a denominator, any points undefined in the original equation will maintain that property through their simplification. Since the original equation is undefined for x equals -3, the simple linear version must also be undefined at -3. The linear equation itself doesn't have any problems with -3, and if we were to graph the simplified equation instead of the original where it came from, we'd find that the hole is filled in. This confirms to us that there should be an answer at this point, and it should be the coordinate -3 for x and 2 for y. But we cannot say that f of -3 equals 2 since f of -3 is undefined. One way we could make this work is with a limit. While f of -3 is undefined, the limit is not. This little equation here is a limit equation, and it reads, the limit as x approaches -3 for the function f of x is 2. Or in other words, as you get closer to x equals -3, y appears to be moving towards y equals 2. This is the true power of a limit, giving us an answer for something that is technically not there. Going back to our tangent line example now, we know that the slope of x squared at 4 appears to be 8, but we can't prove that with just the slope formula. Rather, we will need the limit of a slope formula. Maybe something like this. This may not seem crazy, but it's actually kind of a big conclusion because we've managed to answer one of our 2 major questions for this unit. How can we trick the slope formula to give us the slope for an undefined distance? The answer is by using a limit. We could now theoretically find a slope of a curve at any single point, but we don't quite have the slope of the curve. That is, a single definable answer that encompasses the infinite slopes across the curve. How are we going to figure out this second problem? When it comes to math and discovering new ideas, our best strategy is to look for patterns. If we can turn the pattern into a function, we can also use the function to talk about the set of all answers the equation can produce. To look for a pattern, let's start by finding the slopes of multiple tangent lines for x squared. If we take the limit of tiny slopes at each x value from, let's say, -4 to +4, and round off all of our answers, we get the following slopes: -8, -6, -4, -2, 0, 2, 4, 6, and 8. If we use these slopes as y values and keep the original x values that we put into our equation, we have a set of coordinates that we can plot. The resulting graph appears to be a linear function, y equals 2x. This assumption is correct. The equation y equals 2x produces y values that are actually equal to the slopes of x squared. This means we can finally take down our second challenge. We can summarize the concept of infinite slopes by expressing the slope as a function. Slope functions are so important that they have their own special title, derivatives. Every equation you can think of has a derivative equation that can find the slopes at various points for the original equation. The derivative is unique for each function, but function types are subject to the same rules when creating their derivatives. X squared is known most commonly as a quadratic equation, but it's also known as a power function. In fact, any function with a term or group of terms in the form a times x to the n is a power function. The slope functions of these power functions can be derived by using what's called the power rule. The power rule states that if your original function is of the form a times x to the n, then its derivative will be a times n times x to the power of n minus 1. To translate, to find the derivative of a power function, multiply the coefficient of the term by its power, then drop the power by 1. If there are multiple terms in the power function, say a polynomial, perform this process on each term. It may not be surprising that the power rule has a limitation. It will only give us the derivatives of power functions. Despite this, we actually are able to take the derivative of a lot of different types of functions right now, including a constant, just a regular number, a linear, a quadratic, a cubic, or any higher power, and even rational functions, which technically count as having negative powers, and radical functions, which have fraction powers. Beyond these, the only other functions we have are exponential functions, logarithmic functions, and trig functions. There are different rules that allow you to find derivatives for these, and we'll be discovering them as we move down the line. But for now, let's see if we can figure out how to use power functions, derivatives, and the power rule. That's all. See you soon.